I'm here with three Columbia engineering profs, and my job is literally to say, Shiho, Dan, yep, welcome. What is the most exciting thing you're working on?
Hi everyone, I'm Ip. I'm a professor in the Department of Earth and Environmental Engineering, and we work on the topic of water quality, water treatment, water purification. We do deep tech to develop new technologies to assess new supplies of water, to augment our water supply, and basically secure our water supplies. So in particular, we do separations, right? We take things out from water, we take the nasty things out, we take out contaminants, we take out salt, which is also known as desalination. That is a topic we are very active in, and we also sometimes take out the good stuff as well. And there's good stuff in some waters sometimes. So on desalination, we have developed new technology to extend the way we do desalinations, right we do right now. We have the technology to treat seawater and make that into drinking water. But they are limited at how much salt there is in seawater. If we go any saltier than that, we don't actually have any good techniques out there. So what we do in our lab is to come up with new methods, new approaches to tackle even saltier feeds. And by that, we're able to access new sources of water to augment our water supply. And sometimes there's also good things in there in some of these high salinity feed streams as well. An example is that in California, in the Salton Sea, there is lithium present in there. There's a recent DOE report that came out. There's enough lithium to make hundreds of millions of electric vehicles for the US if we are able to get all the lithium up. So we're developing technologies to cost-effectively get that lithium out so that we have an alternative lithium supply. So that in a nutshell is the water technologies that we work on.
And may I just follow up? So at what stage in this process are you?
So we have a couple of technologies in the pipeline. The one that's most advanced, we have a spin-off company. The company has licensed our technology. They're in the process of designing and building a pilot plant to demonstrate that it works out in the field and not just in an academic lab. We have other technologies that are going through the gears of the IP process.
Oh,
that's true. I guess I should mention Trident desalination. Yeah.
Very cool. So why don't we just do the quick, here's the technology first, and we'll get back to policy drivers and the rest of the conversation. But Dan.
Sure, thanks for having me, Gernot. I'm Dan Steingart. I have the most annoying title here. I see. It's bleeding into the footer. I'm currently the chair of Department of Earth Environmental Engineering. I also sit in chemical engineering and co-direct this thing called the Columbia Electrochemical Energy Center. And this mix between environment, reactor design, and electrochemistry is what brought me to Columbia a few years ago. I also have this weird title, Professor of Chemical Metallurgy. When everybody 20 years ago was going into nanotech, for some reason I was really into metals. And I wasn't sure why, I just thought they were really cool. And what I'm working on now is reliving my youth, and I'm really excited about it because we are designing massive batteries that can simultaneously make enough metal to supply metals markets. And what I'm excited about this area most is that it solves two big problems. One, it allows us to store more than 20 hours of energy at grid scale in significant ways. The second is it solves the problem I faced when I graduated grad school and was working on a metal production technology. Metals producers like increasing throughput until recessions hit, like what hit in 2008, and then they just try to save as much money as possible. So what we hope is that when we are storing all of the intermittent wind and solar with our electrochemical technologies, we can both hedge or provide buffers for metals markets, particularly aluminum and iron, while solving the energy storage problem. And so what most of the folks in the audience might not consider or might not think about is the amount of energy it takes to make aluminum and iron is massive. That gives it the ability to be a battery. And when we think about storing lots and lots of energy, many of you might be interested in hydrogen. Many of my colleagues at Columbia are working on hydrogen, and I think hydrogen has its place. But when I think about long duration, stable, easy to ship, easy to handle storage, it's other than fossil fuels, it's really been in metals because that's the backbone of batteries, period, as you mentioned. So there are a number of spin-outs from my lab that work in and around this space, and I had the pleasure of working as chief scientist of a company, Electra, that visited CBS a few months ago in Boulder that's directly trying to decarbonize iron, and with them we have a new Department of Energy grant to think about how we can broaden this application to energy storage.
And I should say you believed in the technology so much you took a sabbatical, a year long, uprooted your
yes,
family
yes.
to Colorado.
So I see Davina, hi Davina, in the audience, and I have to be very clear, it was a leave because Electra wanted to make sure that they owned the IP. So it was a leave and not a sabbatical. But yes, it was a super productive year and really showed me the opportunities and challenges in pushing the space forward.
Now, while while steel accounts for some 10% of global emissions, cement is another 10% or so of literally annual global CO2 emissions. And Shiho, you were working on decarbonizing that particular sector.
That's right. Thank you. So yes, I work in cement-based materials. So like Gernot was saying, the cement and concrete sector is a huge emitter, accounting for 6 to 8% of global anthropogenic CO2. And if you think about concrete, volumetrically, it's mostly aggregate, so rocks and sand, but then it's bound by a mixture of cement and water. And cement is the key active ingredient. And it only makes up about 10% of concrete volumetrically, but it accounts for 90% of its embodied carbon emissions. So cement is really the problematic component. So we have to change, production so it's less carbon intensive, or we can partially replace Portland cement with alternative binders. So I'm going to focus on the alternative binders because that's the space that we're working in currently. And luckily, this is something that the industry already does. So in the industry currently, and there's specification for this, we use byproducts of other various industrial processes. So the most common ones are ashes, or fly ash from coal combustion, and also slag from steel production. But as we're trying to more aggressively replace Portland cement with these conventional alternative binders, the supply is going down. So, fly ash, we're reducing our reliance on coal combustion. And so coal power plants are shutting down. There are none left in New York State. Slag, we're not quite there yet, but we want to do the same thing, right? We want to change production practices to make them less carbon intensive, recycle more, maybe use one of Dan's technologies, in which case slag would no longer be a material that's available to us. So we have to start actually thinking about alternatives to alternative binders as policies change. And so we're doing work in this area where we're looking at various industrial wastes. So this includes off-specification ashes, construction and demolition waste, which are abundantly available and can meet the demands of the construction industry. And we apply different processing, including carbon mineralization, which was kind of discussed by Heirloom, to produce alternative powders that exhibit the right reactivities where we can replace Portland cement for concrete production. And so that simultaneously reduces cement consumption, but then we can also utilize waste. And so the interesting sort of scientific engineering part of this is that by tuning the processing, we can tailor the products and then control performance. And so if you toss different things in concrete, it's going to behave very differently. So we look at different reaction kinetics, strength gain, flow behavior, and really try to understand the relationship between processing and performance so that ultimately practitioners know how to design with it. And so we're working in this space, and we're in the very early stages of trying to spin off a company.
So no name yet to advertise.
So
actually, so this is one of these more interesting aspects, right? From Bernd earlier today, we heard the positive connections necessary, right? Where technologies enable each other. In this case, phasing out coal, of course, is a good thing. Less slag is a good thing. And now we're looking at some diseconomies of steel. Can you sort of maybe tell us a bit about the policy drivers or the prospects of any one of these technologies, frankly? What's needed to get to the sort of gigatons CO2 scale that seems to be this vaunted threshold that everybody is shooting for? Are there sort of any specific things beyond, again, back to Bernd's keynote from earlier, right? Wouldn't it be nice if we had a $100 per ton of CO2 uniform carbon price? Is that enough? Is that the main driver? Are there other things that are more specifically enabling policies, enabling levers that are crucial to make this technology, your technology, work?
So I can start off by just talking about the concrete industry, sorry. So there's already going to be policies in place. There are some states and cities that are more aggressive. So New York State is one where they're going to start implementing low carbon concrete policies, where they're going to set GWP limits, and you're going to be required to produce environmental product declarations. So there's that push, and of course, as a result of that, that is going to force industry to change. But these are big changes, and producing those EDPs take money. They have to invest in these new materials. You know, the concrete industry is very interesting, where there's major cement producers, like 10 major cement producers make up most of the market, but then the rest is very, disintegrated. So, ready mix producers are the ones that actually make the material and bring them to site. And if you look at New York City, they have to store materials, right? And when you ask them to store a new type of low carbon material, they have to make a new silo, and that's a lot of capital for these companies. And sometimes they just don't have the space. And so these kind of, tax credits, they might not be that significant, but it at least helps these companies go, approach those EPDs, get those EPDs so that they have like a baseline, and also try to invest in some of the changes in infrastructure they'll need to adopt to implement these new technologies. So that's on the concrete side, I think.
So, as Shiho mentioned, concrete has hyperlocal consequences, both in how it's mixed and how it's stored. Steel's a little bit different in that it's been a global commodity for a long time, and unless they're, and this is I want to be clear, this is my perspective. It doesn't represent Electra or anybody else. I think that while a carbon tax is and if it could be uniform and magic and applied, it's a useful aspect. Realistically, it's not going to move the needle for steel anytime soon because it's simply going to be very difficult to tell China and India to price this in, and that's where most of the steel is made. From my perspective, it's going to take a massive amount of direct government subsidy to companies to put the R&D, non-recurring engineering fees into this sector, right? We're talking just exceptionally low margin stuff, really difficult technical problems, very hard incumbents to displace, where conservative metrics for both steel and concrete, the mechanical performance, it's very difficult to say one for one, much harder for Shiho than it is for me in metals to say, yes, this is a one for one replacement. It takes 5-10 years to get customer satisfaction, customer confidence that this is going to be a durable structure. And that's just on the final product once it's one for one. Before then, it takes a remarkable amount of capital just to design, implement, and refine the reactor, only to have to compete with commodity irons and steels at $500, $200 to $500 a ton, depending on what grade you're looking at. Capital markets, as I see them in 2024, are polarized. Yes, there's a lot of great IRA incentives, and that's done a whole bunch, but at 7% plus interest rates, getting the farm down, as I hear you like to call it, is very, very difficult. So I think if we want to do this, just to be very blunt, and we don't want China to do it, to be very, very blunt, then we have to step up the capital from the government in one way or another to get this through. And this involves the uncomfortable conversation of kingmakers. Once it's not just a tax credit or a generalized policy, certain technologies will be biased. It's a conversation that to or against. It's a conversation that we have to have as both technologists and policymakers, because it's something we're incredibly uncomfortable doing in the United States. And within the Chinese government, there's zero discomfort in making those decisions. But in order to get this done, I just think it takes a lot of capital over a lot of time.
Now, Electra, meanwhile, is actually saying, wait, we can take advantage, at least for now,
yes,
of certain other things like stranded iron ore.
Yes, so there's
undercut the market, right?
Absolutely, right. So to invoke sort of what the Electra philosophy is, and that I agree with, there are all sorts of assets that have been overlooked because these fields have been lacking in any R&D for, to be honest, about 40 years. For example, iron. There's an embarrassment of riches for standard processes. Iron grades that are below 55% are considered trash, or iron ore grades that are below 55% are generally considered trash because you can feed, you can get 55 to 60% pretty readily, and to run direct reduction iron, you need 63%, and there's a good amount of that in Northern Europe. That means there's all this leftover iron that's sitting in tailings piles that are simply not being accessed, and that companies will pay you to take away. So that really reduces the cost of the input. And electrochemical reactor design allows you to be out there, spread out over significant areas where electricity is cheap, and you can potentially run these things in a low duty cycle fashion. They can ramp up and ramp down. The flip side of that is that it takes that much longer to pay off the capital. And so you can work very, very hard to get the capex of this plant down, and that's what Electra is grinding at. I mean, it was a real learning experience for me to be part of that. In these other sectors, so my dream vision of making sure that these metal markets can also supplant the supply, the energy market, is going to require a substantial amount of capital, but at the end of the day, I think it will be worth it because it will solve almost all of the climate issues and stability issues while guaranteeing ultimate electricity prices by 2040 or 2050 that aren't increased because of renewables, potentially decreased actually.
Okay, now one challenge, right? So Shiho talks about the diseconomies in the sense that we are running out of fly ash, thankfully, or slag. Presumably, there's a limit to how much of the stranded iron ore is sitting around in Europe and the US or elsewhere. Is this basically a problem for the next Electra? So Electra will be fine, and we are scaling the first startup, but then eventually we are running out of the raw materials that a process like Electra needs?
No, I think this is, I mean, I don't want to speak for Shiho, but I think this is priced into and factored into everyone's core thesis. There is no relying on scarcity, like just period, full stop. In every engineering decision I make in my lab and what we made it at Electra, scarcity and the risk of scarcity and supply chains was and that volatility was unacceptable. To the extent that we were, in many of the papers that I've written, we're willing to pay to have less efficient processes, which is the opposite of standard reactor design in chemical engineering. In chemical engineering, you typically will find these very, iridium, which only falls from the sky, and you use that because it gives you the most efficient use of energy. Electricity has become very, very cheap. Because electricity has become very, very cheap, we have now the ability to say, let's have a less energy efficient process that allows the use of more abundant materials. And when we price in both the CapEx and OpEx on this, even something that is 10%, 15% less efficient from an energy basis costs in as overall cheaper on a levelized cost for its lifetime.
So I think we might have time actually for one or two questions from the audience, unless Lauren, you give me the horrible, terrible idea. But before we do that, what are the drivers?
So I'm going to go philosophical here. I think the philosophical change needs to happen first before it trickles down to economic change. I think what needs to really happen is that we need to have a paradigm shift in our relationship with water. We do not have our relationship with water is poor. We do not value water sufficiently. We do not value clean water sufficiently. As a prime example, how much we pay for clean water that's coming out from a tap is a fraction of countries in Europe. For example, in Switzerland, they're paying 3 times more for their clean water. And even that, in my opinion, is underpriced. Right? There's a lot of externalities that are not being rightly priced into clean water. That relationship with water is broken. There can be alternative bindings for cement. There's no alternative for clean water. Right? It's the one thing that we need that has no substitute. So I think we need to realize that, and we need to be willing to pay more for clean water that's coming out from the tap. We also should be willing to pay more for clean water after we are done using it. Right? When we use the bathroom, we do our dishes, when we do laundry, that water that's been dirtied, that's an additional cost associated to clean it up before it goes into the environment, or potentially even go for reuse. We're also not paying enough for that. And some of these effects are coming back to haunt us now. Right? There's lead in drinking water, there's PFAS. These are some examples of us not valuing clean water properly. So I think that needs to happen first and foremost, and then we can start to see the other relationship come into play. Water itself is not an entity on its own. There's the nexus between water and energy and carbon. If you look at lithium productions, a significant amount of lithium is being produced from brines in the lithium triangle in South America. To produce that lithium requires huge amounts of water. Right now, they are pumping it from freshwater supplies. So they're competing with agriculture, they're competing with municipal use, using that water in order to produce lithium so that we can all transition into a clean, carbon-free economy. So there's that tight relationship there. What is an energy problem? What is a lithium energy storage issue? It's also a water issue as well. So I think we need to have that deeper understanding before we talk about the trickle-down impact onto economics.
Questions? I think we have time for one or two. If questions are literally one sentence and end with a question mark, we have time for 2 or 3. And we have a couple microphones. Anyone? Everyone? All at once. Actually, right here in the first row. So first row first, and then fourth row. Thanks, Brandon. And
Hi, I'm Sunny. I'm from the West Coast Silicon Valley. I did my PhD at Stanford in physics, and I'm in the venture capital community now. I've noticed that, so I attend either from Stanford or here, the academics are fairly aligned in terms of climate change and how to do about it. And I noticed there's this dichotomy in terms of ideas. Like Heirloom is an example where seems to be a really innovative startup that is can get capital as a result of that. And there's the other side where there's more of the great ideas, but they're really struggling with capital. And it seems to me that from the academic community where there's a fairly unified consensus, if we should approach this, especially in the United States, kind of a Manhattan Project kind of style, where we need to heavily subsidize, just blanket subsidize everything, or a significant amount of it. And how do you, who are deep in the academic community, presumably writing grants to NSF and so on and so forth, how would you approach this in the next, whatever, we keep talking about 10 years and 20 years? Again, I want to emphasize that there are, in the West, especially in the United States, because it's heavily capitalistic driven, the venture community will give money to whatever ideas that makes money at the cost of presumably over a huge percentage of really good ideas that will fail because they couldn't get capital, right? That's where the subsidy needs to happen. That's where the kind of Manhattan-style project kind of idea needs to come through. And I think the academic community being so, valuable, right? Historically, Einstein was the one that, driven that back in the days, right? How do you think about doing that for the next 10, 15 years?
What does a Manhattan project for cement, steel, water look like?
Yeah, so I did my PhD at Berkeley, and so I cut my teeth on that philosophy for a bit, and I think it's great. I think the problem we have in a lot of ways, it's not a market failure, but I think it's market incongruity. Technology readiness levels. Everyone here familiar with technology readiness levels? So academics implicitly think TRLs are a ladder. If I'm smart enough, I'm good enough, I get enough capital, my technology will get to the top, if only I do it right. That's not right. That's not right in my experience. I don't think that's right philosophically or empirically. TRLs are a funnel, they're a filter. And we have to be honest about what's not going to work when we learn. And TRL 1 to 3 is crucial. 3 is like, I've got this thing, it's sitting on my bench. If I understand it and anticipate things correctly, I can know whether or not I really deserve 10 or 20 million. This is hard medicine for an innovator, to work this hard on it, to only see a failure point that seems just brutal. And you say, you know what? When I get a good engineer to work on this, it's gonna be okay. So I think that having a system that rewards honesty at that crucial point between 3 and 4, because I don't think it's that there are a lot of good ideas that are unfunded. I think that there is a lack of more capital is always great, and so I advocated for that before. But the overlay on top of that has to be a sense that it's going to be okay, we're not going to cut your funding, you're not going to be denied tenure, you're not going to be seen as a failure. If you honestly say, hey, this isn't going to scale for this reason, and make it clear to the world that that's the case, because the amount of wasted energy I've seen, particularly in students, pushing on ideas that have a clear Achilles heel, despite seeing it because they think, well, I'm not smart enough to solve this. No, there's real physical limitations in couples per Yip's point, per Shiho's points, right? There's real limits on how these things can work together to solve these problems. And it's understanding those and exploiting those limits is how we're going to solve the problem, not blindly hoping more capital can push through. I think a big problem in Clean Tech 1.0 was 10xing from $10 million rounds to $100 million rounds when it was not at all clear those problems were solved. So in addition to the capital and having more capital, I think having a system that said, okay, this is maybe not going to work for these reasons, and being really brutally honest about it. Frankly, it's our job as academics to be that break, and I don't think we're doing the best job.
Okay, so I'm already getting a cutoff, but you have the microphone. You're standing between us and break, Peter, so pressure's on. Short question.
I of course have questions for all 3 of your guests, but I think that Shiho, I'd like to know if there is an opportunity to go for the old fly ash slag pools together by a number of coal producers to find your raw materials.
Yeah, that's an excellent. I'm just going to hold on to my mic. That's an excellent question. So can we go to coal producers and look for more supplies of this
Well, I
material?
remember that the big coal producers and electric companies had these big pools, and sometimes they break free and cause tremendous problems to towns and things like that. And if they would come clean and say where they are, that they might be an interesting place to be able to go and get the material.
Yes, absolutely. So I think that's a really big direction of looking at ponded or landfilled supplies of ashes that are currently off specification, so they don't meet prescriptive standards. But then we're trying to develop more performance-based standards so that we can either beneficiate or change them a little bit so that they go up to current prescriptive standards, or just identify new applications for them that satisfy performance. So we are looking at.
So you need an
existing
EPA standard.
supplies. We need standards. We will need standards to utilize
Thank you.
these things.
Thank you. And break is upstairs, and we're back at 11. So thank you very much.
Thank you.
Here.